Okay, so this is the repeated measures ANOVA for the Chapter 13 assignment. Really quickly, just to go over what a repeated measures ANOVA is. So first things first, we start with what is a repeated measure design. Essentially, this is a design where you're just going to simply use the same participants through different conditions at different points in time. So essentially, you're not really using different groups or anything like that. Everybody's essentially like getting every condition that you can like think of, or the ones that you have. So it's nothing really big. Well, kind of is, but anyways, um, so with the repeated measures ANOVA, it's essentially a one-way repeated measures ANOVA. Specifically, that's what we're going to be doing today. So I'm going to have a predictor variable, which is lighting, and we're going to have participants who are also the same in each group go through each condition and rate attractiveness of the experimenter. Woo! So that's pretty much it. So let's get started. So these commands right here allow me to load up my library. So I'm loading up computes, loading up EZ, loading up ggplot, multicomp, NL, NLME, past text, reshapes, WRS2, CAR, effects, and HMISC. Sweet. So the next thing that we want to do, we want to create the variables. So specifically, it'll allow me to set my variables to a factor. Yep. So then I'm going to make up, well, not make up, we're going to set participants to be a factor. And in this, we have 8 participants, and each level for the participant is 4, because remember, they're all going through 4 different conditions. So we ran that. Lighting, so there's normal, bright, dim, and dark. So there's 4 conditions. They all have 1 level. For each case, so for the total number of cases is 32, because we have 8 people. They all go through 4 conditions. That's 32. So we're going to run that. And then attractiveness. This is just the scores that were provided by each participant. Woohoo! Now with this command, it allows me to combine participant, lighting, and attractiveness all into one data frame. And I just called it long data. So to make sure that everything really worked, so I'm just going to just type in long data. Well, it's here. So I'm just going to run the command. So what we see here, we have all of our different participants in each of those 4 groups, like I said before. So the next thing that we're going to do, we're going to be exploring the data. So the first thing I kind of want to do is bar graphs. So with this command, this allows me to create the bones of the bar graph, and I also included error bars as well. So we're going to run these. Okay. So essentially what we're looking at is the mean attractiveness rating against each condition. So as far as attractiveness rating goes, and just comparing them all to each other, it looks like if the attractiveness rating for bright is around 2.5 or so, whereas the highest would be dark. So this is pretty interesting, but we're not going to just assume that we have something here. It's just a good visual to show like what the data is showing just outright. The next thing that we're going to do is box plot. So the box plot is really good at using to show the spread of the scores, essentially where the median would what the median scores would be. So it kind of gives you a general sense of where the median scores fall for each condition, and you can also compare them to each other. So we're going to run this command. This command allows me to create the bones of the box plot. Let's make sure you can see that there. There we go. Oh, you can only see half of it. I need to make these bigger. Anyways, so essentially you kind of see like a very big variation in median scores, and also with the spreads. So this is kind of interesting here. So as far as as far as conditions go, we still have a higher rating of attractiveness for dark lighting, and then it follows with dim lighting, and then normal lighting, and then bright lighting. So this is something interesting just to look at, but we're not going to just automatically assume anything just yet. And speaking of assumptions, before I even start, I do want to make note that this is fake data. This is not data to show that lighting has some form of influence on attractiveness rating. But that's just something I really do want to throw out there and emphasize. Do not use this data as a way to show that lighting has an influence on attractiveness. This is not real data. Please don't use this as a tool to say that lighting has an influence on attractiveness. So with that being said, I'm moving on. I wanted to throw it out there because I know there's that one person that would do it. And I'm giving a disclaimer. Maybe I should do that at the beginning. I'll do it at the end again too, for that one person. Okay, moving along. So now we're going to do our descriptive statistics. So with this, we're going to get our mean, median, our mode, standard deviation, and all that good stuff. Going to run that. So by using the by function, it allows me to get the different descriptive stats for each group, or for each condition, treatment levels, what have you. So kind of just getting a general sense, we're just going to look at the mean really quickly. So as far as, did I catch everything? Am I catching everybody? Yeah, that'll be just fine. So as far as the mean goes, it looks like dark has the highest mean with 6.875, so 6.88. Following behind it is dim lighting, so 5.0. Following after dim is normal lighting, so 4.75. And then last but not least is bright with 2.75. So kind of what it's the general sense that we're getting is that as far as attractiveness rating goes, the mean attractiveness level was higher for the dark lighting condition as opposed to dim, bright, and normal, with bright being the very much last. So that's kind of interesting just to look at. But we're not going to make assumptions yet about our data and what we think we may find. So moving along, and speaking of assumptions, so the next thing that we're going to be testing is normality. So we want to make sure that our data is not significantly different, because if it is, then we violate normality, and then then the whole world ends. No, the whole world doesn't end, but that's, for some people it does when they don't mean an assumption, and it should. And regardless, we want to make sure we meet normality in every case, because we want our data to be normally distributed in all seriousness. So now we're going to use the by function to run the Shapiro-Wilks test. And so just looking at it, There we go. So we see for the normal lighting, our p-value is 0.22, so that's less than 0.05. That's greater than 0.05. So we can assume that this condition is that this data is normally distributed, and the same goes for the bright the bright lighting condition with a p-value of 0.135. The same for dim with a value of 0.249, so 2.25. The same thing for the dark lighting condition, 3.6. No, not 3.6. 0.367. So 0.37. So that's pretty good. So we can assume our data is normally distributed. So this is great. Now, there is another assumption, and that is sphericity. But I'm going to be doing that particular one and looking at that particular one when we do the easy function, the easy ANOVA function which is about to be done like right now. So with the easy ANOVA function, this is just one way of using. This is just one way of doing a one-way repeated measures ANOVA. In a way, just like all the other ANOVAs that we've done in the past, it has a similar format. So it's essentially like using an ANOVA approach. So something that if you're more keen to using ANOVA or just more so understanding of ANOVA, this is the one that you would really use. So this is my command here. So we're gonna run that. Gonna run this again. Okay. Boom. So this is essentially our one-way repeated measures ANOVA, everybody. So first thing that I kind of want to really look at is sphericity, because for me that's really important, and that's what I told you I was gonna do like 5 seconds before I did this. So looking at sphericity, looking at the Mauchly's, this test for sphericity, and going back to kind of what I said in the previous video, if you watched it, sphericity is a less restrictive condition compared to compound symmetry. So it's essentially just looking at the variances between the difference in variances between groups and holding that they are essentially the same, or not the same, but roughly equal. So like if you were to take, and using the same example that I said before, if you were to take like the scores between each, if you were to use the scores between each treatment level and you calculate those differences, the differences in regards to sphericity should hold roughly the same. So, well, they should have equal variances. Let me say that. That's a lot easier to say. Whew, that was a mouthful. I need water. But anyways, so what we see here, we're seeing that our test has not violated the assumption of sphericity. So we're good. Now, if it was violated, this kind of like makes this is actually troublesome for us, because it can impact how the F value is, or how the F ratio is calculated. And at that point, then we would be looking at the greenhouse. Then we would essentially be looking at I call them the greenhouse geyser. This one. For a correction. And we'd also be looking at